Okay, today we'll be wrapping up this section from taking what we've learned and applying it to applications. So really nothing new, because all the skills we've learned will be skills the skills we use today will be skills that we've already learned. Okay, and we just have to apply them now to applications. All right, so here we have an equation relating. Sometimes underlining keywords and key phrases is going to be helpful for you. X is the number of units being produced. C, or the output value, the Y, will be the cost in dollars. Okay. So interpret the y-intercept and the slope of this line. All right, y-intercepts. How have I taught you to find y-intercepts on the last quiz? We're supposed to replace x with 0. That's what I mean by we're going to use the same skills, just got to apply it to an application. Okay, so it's going to be, now if you want to write y equals mx plus b and have a y, that's fine. I'm just going to keep it c though. So c equals 25 times, that basically means 0 blunders, right? Because they said x is the number of blunders created. Okay, so by plugging in 0 right here, doing the math, I end up with $3,500. It does say interpret that. So you'd have to interpret this, or if it's a multiple choice, you're going to see phrases that have an interpretation of this value. It means when 0 blenders are produced, the cost is $3,500. Okay? When 0 blenders are produced, the cost is $3,500. You might be wondering, how do you have a cost when starting? Well, setting up the machines, there's a lot of overhead before you start producing things, and that's what this cost represents. Okay, kind of a startup fee, if you will. All right, so there's the first part. Okay, let's move on to the second thing that they're asking us. They're also asking us to interpret the slope of this line. Okay, here's the most successful way. My AP Stats students have to interpret slope all the time too, and this is a good way to set them up for success. All right, get back to what slope really means. Remember, slope, by definition, write this down please so you have this format, is rise over run. Okay, well, rise, the technical, really we're looking at a graph. What does rise really mean? It means the change vertically, up and down, the change in y. A lot of times in math we use a triangle to represent change. So change in y over the change in x. Now, look through the directions and figure out what is y and what is x, because it's asking us to interpret it in context. Y is the cost, it's right above here. So this is going to be the change in cost, and the x was the number of blenders. So this is the change in blenders. Okay, write this down, then I'll show you this last step, and hopefully a light bulb goes off. Say, wow, okay, that's why he's doing this. All right, what is my slope? Well, last couple of days in previous classes, we know the slope is in front of, it's already solved for y, right? It's in front of x. So my slope is 25. Write that as a fraction. And now if you do this groundwork, it's kind of hard to mess this up now, because the 25 is going to be associated with the change in cost, and the 1 is going to be associated with the number of blenders produced. So this is how we interpret this. It's usually better to start off in terms of x, by the way. So for every 1 blender produced, we have a cost, or they have a cost, whatever, as long as you're interpreting it correctly. We have a cost of $25. Okay, so for 17, we have another slope-like application problem. So let's go ahead and take a moment to read that. Go ahead. Okay, it makes sense, right? You don't want to have a wheelchair ramp too steep. If it's too steep, people can get hurt. Grandma and Grandpa will be going for a fast ride. right? Nice and slow. That way also pushing somebody up, it'd be pretty tough if it's too steep. It'd be too much weight, okay? So there's code for this, and you got to make sure you have a certain pitch when these contractors do this. Notice right away that this is in 22 inches, the rise, and then this is in feet. So right away, we got to make sure we have the same units of measure. So I'm going to take this 24 feet and convert it into inches. Okay, so 24 feet, and we need to multiply that by 12 inches. And that ends up, I already have this calculation for you, it's 288 inches, okay? So if you want to write it in the diagram there, go ahead, 288 inches for the run. All right, so let's take a look at this steepness. Remember, slope is a measure of steepness. So the slope of the ramp, of this ramp, is equal to rise over run. Okay, so what's the rise? 22 inches over the run, 288 inches. Okay, for slope, the units always cancel out. Okay, and it's just a measurement of steepness. So let's just punch that in. I got my calculator right here. I'm going to punch this in to get that number. 22 divided by 288. We probably want to compare decimals. I could math change it back to fraction for a reduced fraction, maybe 11 1/44, but I'm just going to estimate this decimal to about 3 spots, 0.076. So this is approximately 0.076. Okay. All right, what's the max slope that we're supposed to be comparing this to? So the max slope is 1 over 12, or 1 inch for every 12 inches. So when I compare that decimal and plug that in the calculator, this comes out to be about 0.083. Okay, so we have to compare those numbers. In the end, is the ramp, okay, in this diagram, steeper or larger than recommended? Compare these numbers, we're good. If this number was like 0.09 or 0.10, we'd have a problem. It's too steep. Okay, so the ramp, gotta make a decision, right? The ramp is not steeper than, you could say the recommended slope. I'm just going to shorten this up and say than the max slope. Okay. Okay. On page 28, let's see if we can squeeze in a little, check your understanding here if you have the room. Page 28, there's a checkpoint 5. I want you to read that and see if you can answer that on your own, okay? And just maybe squeeze in the answer right here. Go ahead, give me about a minute or two to do that. All right, so here we go, 32 feet. We got to convert that into inches. Ends up being 384 after you multiply it by 12. Take a look at that ratio and divide it, and we get approximately 0.094. Okay, so comparing that to the max slope of 0.083, this is now too steep, right? It's too steep. So no, it is not. It's not going to work. So I guess what was the question? Exactly. Is the ramp steeper than recommended? Yes, it is steeper than recommended. All righty. Okay, moving on to the next example. Go ahead and read that to yourself. Okay, so write a linear equation. We saw that in the assignment yesterday. So we're going to use those same skills. All right, here's how you can get this set up here. Here's some steps to follow. Copy this down in the success criteria. We want to make some coordinates. And when you do that, if they give you time, time is always the independent variable, or x. So make some coordinates, and time is always x. Once we get the coordinates going, all my steps are going to be the same from yesterday's notes. We're not given the slope, or what's called rate of change, over those over that year. So we need to find that rate of change or slope. Once we have the slope, now we'll have the slope and a point to use. So we'll be using this equation. Okay, go ahead, copy down. Okay, so here's step one, make coordinates. So in 2009, their sales are 49.7 billion. Let's go ahead and just keep it in billions right now and don't add all the zeros. Make sense of that in the end. The next year, 2010, that's time, 50.3 billion. So there's step one, make coordinates of the data. Step two, find the slope or rate of change. How much did they make actually, per year is what we're looking for. So the slope will be equal to y2 minus y1 over x2 minus x1, which is obviously 1 year, right? But I guess if you don't see it, I'll just write it out. So this gives me a difference of 0.6 billion. So it's 0.6 over 1 year. So that's kind of the rate of change. It's increasing by 600 million basically per 1 year, if we had to interpret that. Okay, so in the end, we're supposed to write an equation. Now it's starting to come together, right? If we have the slope of the line and we have a point, we always can write an equation. So using m equals 0.6, I suppose if you want to change it to a fraction, you can make it 3/5, but I'll just leave it like that. And then choose a point. I'll just grab the first point. 2009 and 49.7. On to the equation now. Y minus 49.7 equals m times x minus 2009. Okay. I don't know if all of you guys have calculators working right now, so I'll take you through these steps because I already got the numbers. So we distribute now. So 0.6 times 2009 gives me 1205.4. And move this number over and we'll have our equation. And then we can answer the last question that they ask us. Any questions on writing the equation? Okay, and the last step, I said predict the sales in 2013. In 2013, just got to go back and remember what we made x. Look at x. X is the number of years, right? So that's where I plug it into. And then it'll give me y, the output, the number of sales. Okay, so for the second part, 2013, we want to plug in 2013 right here. So y equals 0.6 times 2013 minus this number. And I just punched it in my calculator. I'm just going to answer the question now. I know how to plug it in. It comes out to be 52.1. So I'm going to give it a dollar sign and call it billion. 52.1 billion in sales. Of course, that's as long as it stays linear and continues and there's no crazy pandemic that jumps out of nowhere. And then it would keep pace with that trend. Okay. All right, there's a good checkpoint 7 too that follows up with that. So at home, you can try that and check it in the back. We'll probably use that as a warm-up tomorrow in class.